Gone. Okay.
Okay, cool. So
Ready.
hello everyone, and welcome to what will be the last class in this overview of computer science that we've gone through over the last 4 weeks, almost 4 weeks, maybe 5 weeks, considering we took a break. I don't know. I think it's 4 weeks. But yeah, hopefully it's been informative and interesting. And you can see that we kind of went from the top of we went from kind of like the bottom of this chart all the way to the top. We kind of went a little bit from the left to the right, and we've ended up with some pretty interesting understanding of how these things work. So today we're going to go cover a few things. We're going to tag team this class, unlike usually where Alex does the whole class or I do the class. I'll just try to review the pieces that I covered. He'll try to review the pieces that he covered. And we'll go from there. Okay, so the first thing we did was we talked about transistors, kind of down here. We talked about this notion of on-off switches, where each switch represented a 0 or a 1, depending on what state the switch was in, on or off. Usually on is 1, off is 0. We call each of these states of being 0 or 1 a bit, right? So a bit can be either 0 or 1. We talked about how you can combine bits into bytes, bytes into words, a word being the smallest unit of, being the largest unit of processing that that a computer can, or a CPU, a central processing unit, can actually process, right? We talked about how these bits can be combined into bytes, which are used for storage. But you can also make processing units out of transistors, right? You can wire transistors together into these things called gates, NAND gates, NOR gates, XOR gates, and you can start building mathematical operations from these gates, which is a combination of transistors together, right? So we covered memory, we covered types of memory, we covered RAM, we covered flash, we covered CPUs, we covered the speed at which these computers worked. And computers are wonderful, they're fast, which is why they can chunk through a lot of data. But we also found that they are fairly unable to do anything without our help. So we have to write programs, we have to write applications to make these computers do useful things. And when we write these applications, they can be written in programming languages, of which there are many types. We covered some JavaScript here. And then we also started talking about some other more abstract concepts like AI and so forth, right? So with that, I'm going to go through a bunch of slides. And so back in week 2, we covered what are the different kinds of data, right? There's numerical data, there's text data, there's data that is a combination of numbers and text. How they're stored, essentially they end up getting stored as bits and bytes, right? But in order to identify these bits and bytes as data or numbers or whatever they are, there are these conventions or these kind of formats that are used where the data is then understood depending on what format is being used. Essentially, the same bits and bytes can be interpreted differently, right? So, for example, a byte could be a number, a byte could be a character. If you're using ASCII, to read the byte and then say, now, what does this ASCII code actually represent, right? ASCII was kind of old, and so it only had 127 possible combinations, 127 possible options, which is, of course, very limited when you start looking at accents in languages or special characters, or indeed even things like emojis and whatnot today. So you need to have a more expanded character set. Unicode is one example of that, where instead of being restricted to just 127, now you can take the total number of characters up to 65,536. This is all great. You have a ton of data, and we ourselves looked at numerical data, text data. We looked at how you store that data. We talked about spreadsheets, which I'll go back and cover again today. And then we also talked about how data in bits and bytes can take a lot of space, right? So in order to be smart about how we store data and how we retrieve it, we introduced this idea of compression, which is where you try to use a smaller representation of the same amount of data. And the trade-off with compression, if you'll remember, was really about whether the compression is lossy or lossless, right? The lossy compression meant that every time you saved the file or you modified it, you lost some of the original value. But the benefit of lossy compression is that it could be pretty small to store a file when you're using lossy compression. Lossless compression is nice because no matter what you do to the data, yes, it's smaller than the original, but you always get back the original data in an undistorted or unblemished way. And so there are some advantages there too, particularly when it comes to things like photographs or audio. If you're a very, very discerning user and you can really tell when some fidelity has been lost, it's really nice to have lossless compression. But still, compression is a very useful thing for so many reasons. Why? Because every resource or every piece of hardware, or indeed bandwidth, right? Internet bandwidth. Like we just, for example, saw Alex's uplink of his uplink, meaning that the data that his home is sending up to the cloud, right? I said your uplink is restricted. What did I mean? I mean that Comcast's capability of Alex's home transmitting data from his home to the broader internet was constrained. And why is it constrained? Because a lot of people are on the internet these days, and during the daytime they're working and doing school, and then in the evening it doesn't let up either, because now people want to get off their computers and take a computer science class, or they want to get off their computers and perhaps watch some Netflix or Disney Plus or whatever, right? So compression is really important, because if we were trying to send this video data or email data or photograph data back and forth without compression, it would take a lot more bits per second, a lot more bandwidth to send across the internet between computers. It would also potentially take a lot more storage space on your disk, on your flash memory or your hard drive on your computers. And so compression is a very powerful tool to do things more efficiently or at lower cost, and yet give us a pretty decent result. So that's the whole idea behind data compression. Let me just stop here and ask any questions so far, because we're going to build on this quickly through this. Today is going to be just a very fast review. Okay, so everyone cool with the idea of bits, bytes, words, different types of formats of data for numbers, for text, for files. We talked about JPEG files and how they are stored, PNG files, which are used sometimes for storing I would say diagrams rather than photographs, which are usually stored as JPEGs or even raw files or bitmaps in the old days. And then you got data compression, what, why. We talked about what it is. We talked about why it is, because it's more efficient. An example of if you want to store a file with different, or a photograph with different levels of compression. Remember the photograph we had of those daisies or those yellow flowers, whatever they were, and how if they were more compressed, they looked more blocky. If they were less compressed, they looked nicer, far sharper. But the trade-off was the file size, right? Another thing about data compression and image storing is you'll recall that what we see visually, right, is a combination of pixels on the screen. And each pixel, if you go close enough to your monitor like this, you'll probably be able to see a matrix of dots. And each dot is an individual pixel. And each individual pixel, depending on the complexity of the monitor, depending on how good the monitor is each pixel is at least 24 bits. Why 24 bits? Because you have R, G, and B that come together, where if we change the intensity of R, G, and B, we can get different colors across the color spectrum. And I want to mention this right now, because we'll go back into some of the image processing things that Alex had taught you guys earlier, right? So how are images represented? Images are represented in pixels. Pixels are nothing but they're there are a bunch of bits and bytes that are interpreted as a photograph, because in the file, someone says in the beginning of the file, the first few bytes of the file will say this is a JPEG. And so whatever program on your computer or your phone gets fired up or associated with looking at a JPEG will know that it's looking at what is supposed to be image data. Remember, each pixel has 3 bytes. So it's going to look at the relative values of red, green, and blue, and then it's going to display that to you on your screen, whether it's your phone, whether it's your laptop, whether it is a Chromecast or an Apple TV for that matter. It really could be anything. And then remember that video is nothing but a bunch of photographs that are stitched together rapidly, and that's how it works. So we talked about images, and we talked about image manipulation, and we talked about JavaScript and how you would use that to manipulate images with some pretty nifty examples. So with that, I am going to go to this next slide and just remind you guys at a high level, and then we're going to cut over to Alex. Alex, are you good to cover some or revise some programming concepts for us? You might be muted or bandwidth limited. You're still not. You're still muted for some reason.
You are muted.
How about now?
Yeah, now you're good, but we still can barely see you. But
okay. Yeah, I don't know why. Probably because we have 3 people using this Meet call tonight, and so we're using triple the bandwidth.
I see.
Yeah,
we can hear you, but it keeps breaking up.
Hello.
Anyway, so I was gonna say, like, if you look,
I'll turn off my video. Need to go. I thought you said you had one more topic.
Oh, I just wanted to very quickly run through this code and then hand it over to you. Well, why don't you do that? I'll turn it over to you.
Okay.
I'll turn it over to you. Go ahead. You can cover this code or.
Okay, then give me just 1 second. Blur exercise. I'm putting up my tab so that I can screen share more easily. Present now, entire screen. There you go. How are you guys seeing my screen now? Hello, hello?
We can see it. We can see it.
Hello.
We can see it.
Okay, so I was preparing a handful of slides taken from some of the exercises that we've already gone through. I think you were intending to present something else, though, which is probably the next slide in tonight's presentation. Is that correct? I don't have that.
I could go through. I mean, I think this is the slide where they're talking about the image algorithm refresh, slide 6. Let me just send it to you real quick in the chat. So it seems like a good time to cut into a little bit of.
Yeah, my connectivity is really bad tonight.
Yeah.
Okay, so yes, so this is what I was working on right now. Okay, so forget this. I wanted to review 2 concepts before we go ahead and tackle the image blur exercise that Sanjay was encouraging us to look at. First of all, loops. Loops are a very important construct that allows us to execute a piece of code on all the elements of a collection of elements. So if we have an image is full of pixels. There's potentially millions of pixels in an image. We want to run code on every pixel in an image. We can use a loop for that. Modern programming languages have a loop commonly called the for each loop, and JavaScript has this construct. Modern versions of JavaScript do. Here's an example. For pixel : img, then a block of code, and then the close brace to indicate that that's the end of the loop. So the way we read this is for each pixel in image, do this. Done. Okay? What does this loop do? Let's read it together. For every pixel in the image, let us invoke the setRed method of the pixel. Let's send the pixel the setRed message. With what value? Well, we are reading the red value out of the pixel and multiplying it by 0.5. So we are decreasing the amount of red in the image. Let's look at what the image would look like if we hadn't multiplied red by 0.5. It would be nice and bright and yellow. But if we decrease the amount of red in this image, it becomes greenish. Okay, that makes sense. So the takeaway from this slide is the structure of the for loop. For every pixel in the image, do this. Done. Okay? Okay. Then the next construct that we presented, and I'd like to work on this with you guys, is the if statement. The if statement allows us to make decisions in our program and do things differently based on a true or false condition. Right? So if I detect that the condition that I'm looking for is true, I will execute the if branch of the if statement. If I detect that the condition is false, I will execute the else branch of the if statement if there is an else branch. Otherwise, I skip the if statement altogether. So this exercise challenges us to make a 1 pixel thick border around an image. If I click run, what happens? If I click run, I'm reading in an image, I'm zooming in, and then I'm displaying the image. Okay? And it's our white cross on black background, white X on black background. So we want to draw all around this image a green border. So the
I'm not
question
being able to hear you.
is, well,
Really, I can hear him very well.
just one person, or
Yeah, I can hear you, Alex.
Oh, it's kind of breaking up, and then yeah.
so connectivity
Let
is
me
potentially
rejoin.
bad. Certainly something's wrong with connectivity. Yeah. I think the last person who made a comment said that they could hear me.
Yep.
I'll take that as a yes. So the first question we have to ask ourselves is, well, what does it mean for a pixel to be part of the 1 pixel thick border around an image? Well, a 1 pixel thick border is going to be the set of pixels that are either on the first row or on the first column, and the first row has y coordinates 0, and the first column has x coordinates 0. So either x is 0 or y is 0, or the y coordinate is going to be the last possible y coordinate. So this image has a certain height. It starts from 0. So say that the image has a height of 10 pixels. If we start counting from 0, what's the last number that we get? Let's try that. 0, 1, 2, let me count. Do I have my camera turned on? I don't have my camera turned on, so let me turn on my camera. Okay, I'll count on my fingers here. 1, 2, sorry, I'm starting from 0, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the last pixel is going to have as its y coordinate height minus 1. And similarly, the last column, the last row is going to have y coordinate height minus 1. The last column is going to have x coordinate width minus 1. Okay, so we have to make a decision about whether to change the color of a pixel, and if the pixel is on one of these 4 lines, 2 horizontal, 2 vertical lines, we have to change its color. So how can we do that? Well, we will need a for loop, which we just went over, and we will need an if statement. So let me show you the solution. There you go. The solution is for pixel and image. So for every pixel in the image, let's look at what its x coordinate is, let's look at what its y coordinate is, and then let's ask the question, is y is equal to 0, or, I beg your pardon, is x is equal to 0, or is y is equal to 0, or is x equal to width minus 1, or is y equal to height minus 1? If any one of these 4 conditions is true, then change the color of the pixel to green. Okay, let's say we didn't do this. Actually, no, sorry. Say we did not execute this last statement. This would be our image. Here, I'm not doing anything, right? I'm checking a condition, but whether the condition is true or false, I'm still not doing anything. Now, here, I'm actually changing the color of the pixel that matches my condition to green. And as you can see, some pixels match more than one condition. The pixels at the corners will match 2 conditions. This one matches both x is equal to 0 and y is equal to 0. This vertical bar, or this double vertical bar, is an OR, a logical OR. It means that the expression is true if at least one sub-expression is true. So x is equal to 0 or y is equal to 0 is true as long as one or the other or both conditions are true. Okay, so this is a non-exclusive OR as opposed to the exclusive OR, which I did present in one of the first lessons. So now we have the combination of for loops and if statements. And with for loops and if statements, we can do some really, really interesting things. So let's go to the next slide. This is the image refresher algorithm from the slide that Sanjay was going to showcase, was going to present. And I've changed the code. If you guys take a look at the original code from the Stanford website, it doesn't work. So maybe I should post this in the CS101 file so that you guys can find it. Image refresher algorithm. Okay, now that works. Where was it? Blur exercise. So what they want us to do here is blur the picture. Okay, this is a very pristine, very crisp image. Let me zoom in a little. Okay, hopefully this shows well enough through screen sharing. You can see a lot of detail in this image, right? The image of the trees is very crisp. You can almost see the needles. And the mountain is very detailed. Now, we want to blur this image. Okay, so how do we blur an image? Well, in order to blur an image, we need to average the color from neighboring pixels. If we take a bunch of pixels that are all close to one another, and we compute the average color for those pixels, and we assign to each pixel the average color of it and its neighbors, then we will have computed a smoothed out where essentially every is bleeding part of its color onto the neighbors. That's what blurring does. So how do we implement that? I am happy for anyone on the call to take the lead here or to show you my solution if I don't have any volunteer. I guess we don't have any volunteer. All right, so I'll show you my solution.
I'd like to venture an idea.
Do I have volunteer? Please.
Given that you have the coordinates of the pixel you're currently on, you just take the average of the RGB values of the 4 adjacent pixels.
Well, we'd like to use all 8 adjacent pixels, but that's a minor detail, right? We could do that. We could actually do that.
You could, right. I wasn't imagining the diagonals, but yeah.
Yes. So the Stanford instructor is providing little bit of code that we can take advantage of. And one of the things that she was providing is a function that allows us to find the neighbors of a pixel. It's called getNeighbors. So we can do something like this. For neighbor in pixel get neighbors. Okay. Let's see, this should still work. Get neighbors is not a function. Great, did I misspell it? No, that's not how it works. Sorry, my bad. It's img get neighbors of pixel get x, pixel get y. And there you go. So now we have a for loop that allows us to look at all the neighbors, all the pixels that are in the vicinity of the current pixel. The current pixel is this one, right? For every pixel in the image, do something. Now, for every pixel in the image, we are doing this, which is for every neighbor in the list of neighbors of the current pixel. So now that we have a for loop within a for loop, it's called a nested for loop, what do we do? What's the next logical step here? The next logical step, like I said, is to borrow color information from all the neighbors, right? Here we're using the color information from one pixel, but we really want to use the color information from all of the neighbors. So let's set this all to 0, and let's start grabbing information from our friendly little neighbors. So red is going to be equal to red plus neighbor get red. And green is going to be equal to green plus neighbor get green. And blue is going to be blue plus neighbor get blue. Okay, now if I have not typed anything wrong, what am I doing here? I'm accumulating in red the sum of all the red channels of all the pixels in the neighborhood. And in the green variable, I'm accumulating all of the green channels of the pixels in the neighborhood. And the blue variable contains the sum of all the blues, right? Why am I saying that it contains the sum of all the blues? Because I'm repeating this addition for every pixel in the neighborhood, okay, for every neighbor. So we're starting with red is equal to 0, green is equal to 0, blue is equal to 0, and then for every neighbor in the list of neighbors, I'm adding to red the red value of that pixel, and I'm adding to green the green value of this pixel, and I'm adding to blue the blue value of this pixel, which means that after I've done this for every pixel, red is going to be the sum of all the reds, and green is going to be the sum of all the greens, and blue is going to be the sum of all the blues. So what happens now, right? If I just click run, what happens? Do I have a hypothesis? I'll just show you. It'll take a while. This is a very inefficient way to do image manipulation, but we are patient. What are you seeing?
White.
There's a lot of white, and there's some yellow, and the yellow that we're seeing is very yellow.
And like some brownish black.
And there is some brownish. What's happening here is that we are creating pixel values that are way too high. because we're adding up 9 pixels, right? All the pixels within a 3x3 square, we're adding them up. Now, pixel values are supposed to have color values, or the color values within pixels are supposed to be between 0 and 50. Any pixel that is sufficiently light, like a light blue of the sky or a gray of the mountain, is going to be on average above, say, 100, maybe even above 150. We're adding 9 of those pixels together. Well, what do you expect to get? You expect to get a number that's going to be greater than the maximum possible value of the color of a pixel, which is 255. And if the color is above 255, it's going to be displayed like 255. It's going to be displayed as the full, complete intensity of that color. And when you have the full, complete intensity of both red, green, and blue, what do you get? When both red, green, and blue are maxed out, what color
White.
do you get?
White. No.
You get white.
White, yeah.
So you get white. So this is what we're getting here, right? We're getting a lot of white. So what do I need to do to fix this? Bear in mind, I'm adding up all the reds, I'm adding up all the greens, and I'm adding up all the blues for the 9 pixels within my neighborhood. What do I need to do? What I want to do
You need to add.
is I want to compute an average. Right? I said in order to blur an image, I want to compute the average color within a neighborhood. But I'm not computing an average here, I'm computing a sum. So how do I compute an average?
Who knows? It's a very complicated mathematical operation, I think.
Okay, let me come to the rescue.
You do like the 3 colors.
N pixels, or n neighbors, is equal to 0. We start with 0 neighbors, and then every time we find a neighbor, we add 1. N neighbors is equal to n neighbors plus 1. Now I have a number of neighbors. Well, now that I have a number of neighbors, I can compute the average. How do you compute an average? You sum up all the numbers, and then you divide by the number of numbers. Right? This is the average red, the average green, and the average blue. And there you go. Now the blue looks blue, it doesn't look white, the gray looks gray, the green looks green, and so on. Okay, let me zoom in, let me prove to you that we have actually blurred this image. Hopefully you guys can see the details from my screen. This is the detailed image before we blurred anything. And this is the blurry image. Does it look different?
I can see the difference. Yep.
Does it look different at all?
Yeah.
Yeah.
I'm hoping that you guys can appreciate this on the call. It looks different from perspective. This is a very coarse approach to filtering. It does not allow me, for instance, to decide how many pixels I want to consider when computing this average. With this technique, I can only do a 3x3 square, so only 9 pixels. In general, in order to do a good high-quality filter, I want a lot more control over how many pixels I use and how I weigh, what kind of weights do I apply to these pixels and so on. But at least this shows us how to use a nested loop to accomplish this task. Okay, and I will copy this to in the CS101 agenda.
All right. Let me take over again, or you want to keep going?
Okay. What next?
We can switch to...
Sanjay, do you want to take the example again, or do I continue?
No, I can continue. Can you hear me?
I assume Sanjay wants me to continue.
I don't know. I'm talking. Can you hear me? Can anyone hear
So
me?
what's next?
Can anyone hear me on the thing?
Yes, I can hear you.
Sanjay, did you
Okay.
take control of the screen
I
share?
can hear you.
I did. Yeah, everyone can hear me. I think you're having
Alex, you
some
don't seem to be able to
difficulty.
hear us. We can hear you. Yeah, I cannot hear anybody at this point.
Okay, I'm gonna take over.
Excellent.
Let me do this. Okay, so thanks to Alex for that, for revising JavaScript concepts, image manipulation concepts, and now we'll turn to spreadsheets. So you guys remember spreadsheets were a way of manipulating a lot of text data. And actually, let me just do this real quick. Let me just see if I can grab those spreadsheets that we had, because that might just make it a lot easier for us to, yeah, here we go. Is that now screen? Yeah. So you guys remember spreadsheets were this representation of a large amount of data, right, which you can see over here. And this was an example of about 12,000 Marvel comic heroes or characters. And we were able to go through this. We were able to classify these by using this a series of different commands. There was one which was called unique, which allowed us to extract how many unique elements were there within a single column. Based on the unique, you could go through with a bunch of functions. Many of them are called the ifs functions. So you'd go, count ifs. You could count number of different types of characters. There's a ton of things that. Oh, poor Alex dropped off and can't seem to rejoin. Oh, yikes. Okay, keep trying. I got it for now. Let me send him that. Okay. So so that's where we are with spreadsheets, and you could see that thanks to having these really powerful commands, which are the ifs commands, you could do a bunch of things, right? You could go count different types of characters. You could try to find out, what was the what were various characteristics of these different characters based on the criteria, based on the types of characteristics that each of these characters actually have, and that can be pretty powerful for understanding data, for manipulating data. So that was a really cool example of how you can use spreadsheets. If you want to understand something about additional commands, you can go to Google. You can type count ifs, Google Sheets. It's a great way to just get quickly to the help of those sheets. You can see that there's a bunch of math functions that are available. These are related ones. There you go, Alex, you're back. And so there's a whole bunch of possibilities here, depending on what exactly you're trying to do. So when you're trying to do something in Sheets or in Excel or any other spreadsheet, spreadsheet manipulation or spreadsheet processing tool, remember that there's no need to have a memory or remember every single one of these commands. Instead, you can always go poke around in the help to try to understand what options you might have available to you, and accordingly, you'll be able to find a lot of goodness in the help files and make progress with spreadsheets. Spreadsheets are really useful because you can store them you can use them to store a ton of data. You'll of course notice over here that the type of data that's being stored here is mostly numerical and text. When you start getting to more complicated storage mechanisms for data, we call those things more generically databases. And those things can be used to store all kinds of data. So if you think about a Snapchat profile or maybe a Facebook profile, in addition to having some basic information about you, you also have other information like your photographs, videos you may have posted, things like that. Obviously, all those things are ultimately associated with your account. And so there's some security things that we talked about, right? When you log into a server, there's authentication. We talked about passwords. This all came later. But ultimately, you're trying to get to the data, and you're trying to go grab that data and query that data so you can make sense of it, and then thereby get on with whatever it is that you're trying to do in that particular program. Right? Alex, you want to try talking to us now? Can you hear us or no? Hey.
Yeah, I am on my cell phone now. I'm trying to regain control. I think it's an issue with my Chrome crashing.
Oh.
So
okay.
You could just continue on your merry way.
I will continue on my merry way. Okay, so let me then go down to this next section on AI. And by the way, I want to point out something. So in the document, right, there's a bunch of stuff in this what we'll cover section, which has a link to some notes files, okay? So for example, if you click here, there's a lot of detail on everything that we covered in the class, where you can actually go through it and refresh it if you ever want to get a quick refresher. And then that way you'll be able to remember from everything that we did, what exactly were the things that we covered, right? So this may be a great article to read about AI. This is kind of a good thing to read now that we covered artificial intelligence. Okay, so with that, let me go to the AI section. I did not teach the section, so I'll try to cover it real quick, since Alex is still trying to fix his stuff, and then we'll go to internet and we'll keep going until Alex comes back, okay? Okay, so we talked about AI, we talked about data, right? Data is stored in databases, right? Especially if you have complex data that's comprised of numerical data, as well as text data, as well as image data. And you can imagine something, we talk about smart this and smart that. One great example, which I like to think about, is self-driving cars. And what is AI, essentially? AI is the ability for computers to go process a bunch of information and essentially classify it, right? It says, hey, should we go left? Should we go right in the case of a car? Should we stop? Should we not stop? Should we accelerate? Should we decelerate? Right? These are the decisions that are typically made by a self-driving car. And you can imagine each of those decisions simply being ultimately a classification of a bunch of data that's being consumed by the computers in real time, right? And the computer algorithms have to go through this data and make a decision, make essentially a classification decision, which is machine learning. And that's where the computer is trying to throw a ton of variables into a model and say, hey, what do I need to do as a result of this? Okay, so artificial intelligence. We started with this idea of there's two types of essentially machine learning that you have. There's something called supervised learning, unsupervised learning. Supervised learning is I have a bunch of data of the past. So for example, I have the price of all houses sold in San Jose over the last year, and now I'm trying to make a prediction of what house prices will be in the future based on the past data, right? This is where I had data. I'm looking at the data I had in the past. I'm trying to make a decision. That means I have supervision for understanding what that data actually is. And so that's one way of looking at it. Another way is where I don't know anything about the data. I'm going to inspect the data with an algorithm. I'm going to try and start to make sense of it. And this is where you have more complicated algorithms for artificial intelligence, which are called unsupervised learning algorithms. Or if you have a bunch of machine learning and artificial intelligence going on, then you start talking about things like deep learning and neural nets, which is just more complicated stuff, right? So Alex, you want to take over again since you're back and just jump back into the AI piece and finish this up maybe in the next 5 minutes or so, and then I'll switch to the next topic. We can't hear you.
Will you continue presenting so I can just talk over the slides?
Absolutely.
Yeah, so a lot of what artificial intelligence does is learn about the statistics of a complicated data set, right? Supervised learning is where you have some descriptors and you have some outcome, and the descriptors and the outcome are kept separate, and you want to learn to predict the outcome based on the descriptors. And unsupervised, you don't have a separate piece of data called the outcome. You just have descriptors, and you just want to come up with a fancy statistical model about this data. So a lot of what we do in machine learning and AI is more or less complicated statistics. Now, the great old Alan Turing, and we talked about him, what was that, yesterday, I think, he asked the question, what does it really mean to be intelligent? We can reason about a machine being intelligent. What does it really mean? And he came up with this definition. A machine can be considered to be truly intelligent when, if we set up a dialogue, a conversation between a machine that runs an artificial intelligence algorithm and a person, that person would not be able to distinguish the machine from a human, right? That's the Turing test. So Turing test more generally is the term that's used for techniques to determine whether something is a machine or a human. And if a machine is able to pass the Turing test, then it's really, really intelligent, right? It really understands what it's doing. Okay. Can you please move to the next slide? Okay, and we talked briefly about machine learning. There are different techniques in machine learning. There's lots of different techniques in machine learning. For the most part, machine learning, like I said, is about building statistical models of the data. If we talk about predictive modeling or supervised learning, we're looking to predict a variable based on any number of other variables. One of the techniques that we can use is regression. Regression is any one of several techniques to estimate the expected value of a variable based on whatever else I know about that variable, right? Whatever else is already known to me. So if I know the descriptors, what is my expectation of what the value of the outcome will be? Now, so regression can be, we can estimate the mean, the expected mean, or we can estimate the median, or we can estimate, some other measure of central tendency of a statistical distribution. Those are all techniques called regression, right? And linear regression, you probably will study at some point in school, is the simplest of them all. And though it's the simplest technique, if it's done well, it can yield impressively good results. Linear regression is based on the idea that I can model the outcome of an experiment based on a line, okay, or something slightly more complicated than a line. What is a line? Some of you may have studied lines in, the algebraic expression of a line in math class. You may have studied things like y is equal to mx plus b. Okay, that's a line in one variable, one descriptor variable, x, and one outcome variable, y. We can slightly generalize that and say that y is equal to m1 x1 plus m2 x2 plus m3 x3 plus b, right? And we can have any number of x's and a number of m's. That's linear regression. Okay, it's simple, but it can be very, very powerful if done well. And other techniques, grouping is probably the first one that ought to be mentioned, but it does appear first in these slides. Grouping is the idea that if I can identify a bunch of examples that are similar to the one that I'm looking at, I can just find the most likely outcome by looking at the outcomes in my set of examples. So when I've collected a data set, potentially thousands or millions or billions of examples of data, of records, and now I see one example. If I can find a handful of records in my data set that are close enough, that match somewhat the example that I'm looking at, I can look at the outcomes in those examples, and that's all my model is. So this is called nearest neighbors, and it's a very, very powerful technique. And it kind of, if this works, it's the best one in general. Natural language processing is about learning or allowing a machine to learn language. It has gained tremendous popularity in the last few years with products like Alexa and Google Home and the Google Assistant. You know, learning to recognize your voice, learning to understand what you're talking about, and learning to execute commands. So there's multiple layers of machine learning and AI involved in a product like that. For one thing, there's the recognition of sound, and then there's the recognition of words, and then there's the recognition of sentences, and then there's the recognition of commands, and so on. So very, very powerful techniques. And these are the kinds of products that could actually legitimately win in a Turing test and come across as being humans to a human, which is kind of scary. And then possibly the most impactful technology in the next 10 years is going to be computer vision, and particularly as it applies to self-driving vehicles. In order to drive a car around, we rely a lot on our eyes, and that's why we have to take visual acuity tests every once in a while at the DMV in order to be given a driver's permit. We'll have a break in a short while. Now we are having cars that have lots of cameras. They have way more cameras than we have eyes. And they could ideally recognize what's going on around the car a lot better than we humans can, just because they have more eyes. So the ability for a computer to recognize a car and estimate the distance of a car, and recognize a human walking along the street, and recognize somebody on a bicycle, and estimate the distances, and estimate how long it would take to get there, and whether we need right now to slow down in order to avoid bumping into them. That's a very, very powerful application of AI in the context of computer vision. How many slides do we have left in the
Not a
AI
lot.
module?
I think it's basically just a few.
Okay. And then robotics is possibly the most fascinating application of AI. Robotics is a lot more than just AI. Robotics is about building machines. So, you know, a lot of the ingenuity goes into the mechanics of a robot. But in order for a robot to do really amazing things, it needs to have fancy algorithms to allow it to recognize where it is, recognize what objects are around it, and how to interact with them, and so on and so forth. So robots might need a combination of the type of AI that allows them to recognize objects, so computer vision, but also the ability to plan, you know, to make a plan. Like, how do I get from here to there? That's not something that you learn using supervised learning or unsupervised learning. That's something that requires completely different algorithms that were actually trendy and were being studied 50 years ago at the very early age of AI. Is that the last slide in our presentation on AI?
Yeah, I think we need to breeze through this because you covered it before. So, yeah. So I think AI is obviously a very important branch of CS, computer science. I am going to move over here now again and restart the recap presentation. So that was the conversation. Sorry, go ahead.
Can we take a break really quick?
Sure. 2-minute break and then come back. So I'm going to barrel through this, Alex, until we get to the last slide on theory. Then you can pick up again. Okay. Alex, I'm going to barrel through all of these until we get to the last one on theory. I don't know if you can hear me. Can you hear me, Alex? Can you hear me?
I can hear you.
I don't think you can hear me.
If anyone's talking, I can't really hear them.
We weren't talking. Can you hear me now?
Yes.
Okay,
Yeah.
good. Yeah, no one was talking. We seem to be having some issues with Alex's audio, so I am going to. Oh yeah. Alex. Okay, Alex. Yeah. Okay, so I'm going to get started again. Hopefully that was a quick and good break. We just want to get through this stuff, so we'll go through it. Okay, so we covered AI, and everything we covered until this point in the course was about computers, algorithms, software, classification, data manipulation, et cetera, et cetera, et cetera. Wonderful stuff. Essentially, all working on one computer, right? But as we all know, and certainly as all of us are experiencing right now, we're all on different computers or different devices. Some people may be on mobile phones. Some people may be. Interestingly, I took a look at the YouTube video statistics, and it seems like a lot of people have watched the YouTube videos from their iPhones. So that's kind of cool. The point is, computing today is useful to us because it is distributed, because computers can talk to each other. The computers do not have to be physically wired to each other. They don't have to be in the same place. They can literally be anywhere in the world, as we know, because especially these days, being home, the ability to communicate is so important and so awesome, right? Typically, a computer that receives information is called a client. One that sends it is called a server. Notionally, when we think about computers, we usually think about bigger computers having more stuff. And so even though those computers receive things from us as well, like, they receive data, email, whatever, we tend to call the bigger computer servers and the smaller ones clients. But actually, algorithmically, anything that is consuming is a client. Anything that's sending is a server. But let's not worry too much about that. Big computer server, small computer client, life is good. How do these things communicate with each other? Well, they have to have a common language, right? And so at the very lowest level, there's a physical communication, which is sending electrical pulses over a wire, or changing the intensity of radio waves, which can get interpreted by very complicated radio circuits and radio processors, i.e. Wi-Fi. But those bits and bytes that are changing in a physical sense ultimately get encoded or get converted into a stream of zeros and ones, which then can fly across computers over the internet. And so they communicate via a protocol called TCP/IP, which stands for Transmission Control Protocol / Internet Protocol, right? And an IP address, if you guys will recall, is a unique 32-bit address that is provided to every single household on the planet. In fact, every single device on the planet, but at least every single household. And then your router in your house takes on the responsibility of farming out that external IP address to additional internal IP addresses within your own homes, and then also keeps track of, hey, this application has requested the data, so that you don't send your video data from Google Meet to Facebook or something like that, right? So there's these protocols that kind of make sure everything flies through in an ordered way so that the right applications can receive the data back and forth, so on and so forth, right? Something that is a processing element that we don't necessarily see directly, but it's a bunch of computation or management that's done in the background. It's called a backend, right? And so when we talk about a Google backend or a Facebook backend, we're talking about all the processing and algorithms and computation that get done in a Google or Facebook cloud. And again, a cloud is just conceptually a computer that isn't physically with us right now, right? It could be anywhere. Like you could even have a cloud in your own house if it's a different computer other than the one that you're using. But we think about the cloud conceptually as being large farms of computers that are clubbed together for specific purposes. And some fine examples of this are companies like Amazon, Web Services, also called AWS, which is essentially a commercially available set of cloud computers that are instantiated or replicated around the world in these massive buildings called data centers, which have massive cooling requirements and electricity requirements. And these things, obviously, because they're so big, are usually somewhere in a less populated, cheaper place. For example, Google has a data center up in a place called the Dales in Oregon, and we probably have tens of data centers around the world. And these things are all connected together using fiber optic cable, which works at a bazillion gigabits per second, connecting all these different computers together across the world, right? So that's how these Facebook and Google and indeed any large company backends work. Just as a matter of trivia, since you guys know this, know these concepts already now. Interestingly, a large company and many large companies, like for example, even Netflix, don't have their own data centers. They in fact rent computing power from Amazon Web Services, AWS. Microsoft similarly has their own cloud services. They call them Azure, Azure, which is Microsoft's cloud. Google has something called GCP, Google Cloud Platform. And those are kind of the big cloud platform or big cloud companies in the world, where if you're trying to start a distributed service, let's say you're like a DoorDash or something like that, right? And you don't want to invest in a bunch of infrastructure, and you still want the quality of service and the responsiveness of a great application or web experience. Why build all this stuff? Differentiate with your application, which is the DoorDash, but leave the infrastructure to somebody else, where in fact you can probably even get it cheaper because you don't have to take on the big fixed cost of building a building and running fiber optic cable. And indeed, you may not even know how to do that efficiently, right? Large companies can do that far more efficiently because they have the know-how and the money to do it. What's HTML, CSS, and JavaScript? Really quickly, HTML is an old way of writing web pages, hypertext markup language. Some of you guys wrote some HTML, which was kind of fun. It's essentially a tagged language. Somebody wrote some HTML, which was generated, and so you saw a lot of spurious HTML. But imagine you had a website like this one, which had multiple pages on it. You wanted to make a formatting change. So there was this thing called CSS, which is like color style sheets or coding style sheets. I can't remember what it stands for. But you could essentially change the template, and you could now have changes propagate effectively through your entire website. And Alex talked to you guys about that and how to go manipulate the CSS on the fly in the debugger, which was quite a bit of fun, which you could just get to the debugger, of course, by simply right-clicking and then just saying inspect, right, which was a really powerful way to get to the JavaScript, or a JavaScript debugger, but the JavaScript debugger that happens to be in this version of Google Chrome, which is what I'm using, right? JavaScript is one programming language that happens to be supported by most browsers. All these things work together. How? Because JavaScript's in the browser, CSS is supported by the browser, HTML is supported by the browser, the code sits on a server, we go grab it from Stanford using a URL, we get this code. This URL, remember, is translated to an IP address using DNS, or the domain naming service, which we covered. And that's how this whole thing glues and connects together with a series of protocols, which are TCP/IP, IP addresses, domain naming services, URLs, and of course the tools that are used to build the front ends, which is what we interface with, which connect with the back ends, which do the processing. Okay, so we had the guest lecture by my buddy Charles, who talked about design, and he talked about the back scratcher, and he talked about how you gather requirements and how you start thinking about what is the problem you're trying to solve. Why is design important? Because design, of course, leads you to cues which tell you how a product ought to be used. It should be obvious to somebody when they look at a product how to use the product, which means that the product has the right affordances, as they say in HCI language, which means here's what this product allows you to do or affords you to do. And so that's an important term to learn from in the HCI world. What's a sign of an affordance? It's like saying, hey, if I have this pencil over here, oh, sorry, I just realized my video has been off all this time. But if I have this pencil over here, fortunately, I wasn't showing you guys any visuals until now. But if I have this pencil over here, right, I mean, clearly looking at it, there's some important signifiers in this pencil, right? I mean, clearly there's this tip over here, which seems to be something that is more pointy, and therefore I've learned that this is something I should write with, right? And then this side is the eraser. Now remember, this is a learned thing for us, right? Because if somebody handed you a pencil when you were 2 years old, you might just put it in your mouth, right? You might not know that I got to write with this, because you don't even know what writing actually is. So a combination of knowledge, expectation, signifiers, affordances come together to build a product, and the interfacing of humans with that product. And if you're not careful, you can do some pretty silly things, right? And so therefore, HCI is actually very much a science and an art, where designing elegant interfaces so that we can pretty obviously understand what to do, right? In fact, in a day and age of touch screens, which you kids have grown up with, it's kind of lame, for lack of a better word, when a monitor these days doesn't have a touch screen, right? Because you want to kind of go and manipulate the text or the data with your finger, because it feels like a natural thing to do. Maybe it's learned, but it also feels like a natural thing to do, right? For you guys who are curious, go online and go to YouTube and look at Steve Jobs revealing the iPhone in 2007. And he talked about how God gave us the most amazing pointing device, which was right here. And what they're saying is essentially that for different applications, they want to change the user interface. So they did away with physical keyboards, and they built this amazing evolving surface, which can change based on the specific application. It can become something different depending on what you're trying to do with it, right? So that's the beauty of HCI and the criticality of it, frankly, right? If you have a product that is really hard to use, you will know it. And actually, increasingly, we are getting away in product design from this idea that if you can't use a product, you're not stupid, the product's stupid. Because why should you have to learn something unnatural, right? And this is a very important realization that has happened in the last 5 years or so, I would say, maybe 10 years, but definitely last 5 years, saying what used to be important from a specs and megabytes and megabits and RAM and flash and all these things. Yes, those things are very important, but what's more important is that the product does what it needs to do, right? And that the user who uses it understands, thanks to the ingenuity of the designers, what exactly this thing is meant to do, and that it actually does it in the right way. And that's what sells products, right? Not something that has a crazy spec, but something that works well these days, certainly. Okay. Security and privacy. I don't know, Alex, is your audio alive again or no?
Can you hear me?
Yeah, we can hear you. You want to quickly go through this?
Yeah.
I can pick up Bitcoin, or you can do Bitcoin today, either way.
No, I'll let you talk about Bitcoin. Otherwise, I'd be very negative about it. What is the difference between security and privacy? So privacy is our desire to keep our personal information to ourselves and not let people who don't need to have access to it, and we don't want them to have access to it, to gain to illegitimately gain access to our information. That's privacy. Security is a set of technology and practices to defend our privacy on the one side, so to defend our information from access from people that are not authorized, but also to protect our assets from, for instance, our financial assets from being taken through illegitimate means through the use of technology. So we care a lot about privacy and security in computer science. So from the perspective of software developers, they need to ensure that their software protects the privacy of the user, that it doesn't take information that it should not have access to, and that it does not divulge this information in an unauthorized way. Developers are also very interested in creating applications that are not open to illegitimate access, and that's a security aspect of technology. And then there's processes and practices like having a good password, having a long password. We did the math in real time a few days ago when we talked about this, and I discovered that my passwords were too short. I used to use 32 characters to my passwords, and by doing the math with you, I discovered that I actually need 49 or more characters in my password. So I recently upgraded the length of my passwords to 50 characters. And I use a password generator and a password database, an encrypted password database, to store all my passwords. So I don't have to remember them, and I don't need to use any trick to remember my passwords, right? I just need to remember one, which is the password to my password manager, and that's it. We also talked about encryption. Encryption is a technique, or any number of techniques, to scramble data in a way that allows it to be unscrambled. So encryption algorithms, in combination with some key, create a one-to-one function between clear text data and ciphertext. Clear text is the unscrambled data, and ciphertext is the scrambled data. And it's important that the data can be scrambled and then unscrambled, otherwise encryption is useless. So encryption, the security of encryption depends on the security of the password, as usual. It also depends on the security of the algorithm. There are algorithms, and we presented a few, that use two keys, a private key and a public key. The idea is that you can share the public key, but you have to keep the private key for yourself. These algorithms were considered to be very, very secure 10 years ago. Now, with the advent of far more powerful computers, but more importantly, with infinitely more powerful computers like quantum computers, these techniques are no longer considered secure, because a quantum computer could take my public key and do the math to figure out what the private key is that matches my public key. So if somebody has my public key, and if they have a big enough quantum computer, they can unscramble all my communication, which is a problem. So newer encryption techniques are being developed that are robust to quantum computers. There's another technique to scramble data that we described. It's called hashing. Hashing, unlike encryption, allows you to scramble the data, but it does not allow you to unscramble it. The purpose of hashing is to be able to determine whether two inputs are the same. If one input generates a certain hash value and another input generates the same hash value, then I can, under some conditions, conclude that the two inputs are the same, or at least there's a very, very high probability that they were the same. Why is this important? Because it allows me to make comparisons without actually having a copy of the data that I'm comparing. This is very important for passwords. Companies like Google don't want to store customers' passwords. They want to store a hash of the password so that when the user logs in, they can compare the hash that they have stored in their database with hash that they are computing from what the user is typing in. And if the two hashes match, the user has access to the real password. The user is hopefully the right person. But Google does not keep a copy of the password. It would be a big violation of our privacy if Google or Facebook or anybody else actually kept a copy of our passwords. Does this mean that every company uses hashing? No, there are companies that are not secure, that are not respectful of their users' privacy and are actually storing passwords unscrambled in their databases. That's very, very bad. But unfortunately, it happens. So how do people get illegitimate access to your data? More often than not, it's due to users having a weak password, having too short of a password, or having a password that is a common word. How common does it have to be? Well, even very uncommon words are common enough passwords. And I've shown you a database of several gigabytes worth of passwords that are known to bad guys, that have been stolen already. So if your password is one of the passwords that has been stolen already, somebody will be trying it in your Google account. Somebody will be trying it in your Facebook account. And they have to be very patient. They may have to try 100 million passwords, but it's still easier to try 100 million passwords that are known to have been used already, rather than to try 100 quadrillion passwords at random. Okay, because the number of total possible passwords is unbelievably large compared to the list of passwords that are known to have been used. And I showed you my very secure passwords, 123QAZ. How many times had that been used? Do you remember? That password had been stolen 57,000 times. So it's, it seems like a pretty nifty password. It includes both numbers and characters. It does not include any word. So one would think, hey, that's probably a secure password. Actually, it's been used and stolen 57,000 times. So then I said, okay, well, let me add an exclamation mark. Now it's really secure, right? Now I have punctuation marks, numbers, and letters. It's got to be super secure. Even that had been stolen at least a dozen times. I forget the exact number. It wasn't in the thousands, but it had been used and stolen several times. So what's the only secure password? The only secure password is completely random, generated by a well-designed, well-crafted password manager, and copied and pasted from your password manager into the website that you're logging in. As of a few days ago, I have come to conclude that you need to have at least 50 characters, including uppercase, lowercase, and numbers. I avoid stranger characters than uppercase, lowercase, and numbers because they get hard to type, especially when you have multilingual computers, and many of us are multilingual. So how else do criminals access data? Well, they access data through bugs in software. There are companies that are notorious for the bugs in their software. Companies like Anthem Blue Cross and Equifax have allowed bad guys to steal tens of millions or possibly hundreds of millions of social security numbers. And that is very risky because bad guys can use social security numbers to file tax returns and create all sorts of trouble for the person affected. Unfortunately, we can't actually do anything on our side to protect against bugs in software that we use, but we have to be selective. We have to use only software that we have reason to believe is safe. Google spends a lot of effort in making its software safe, and yet it is still possible that they may have a bug. But companies that do not put as much effort in making their software secure and robust, we should not do business with. That's really the measure of protection that we can take. And then back to Bitcoin.
Yeah, so actually an interesting segue to Bitcoin. So we did the Bitcoin class on Monday or Tuesday, I can't remember when. I think it was Tuesday. And yesterday I had a rather scary thing happen to me, which is I got an email from someone I didn't know saying, I have your password, right? And this has never happened to me. This is what a coincidence, right? And I'm sure it had nothing to do with teaching the Bitcoin class, and I'll explain why. And if you don't pay me $1,000 in Bitcoin, then I will, reveal some passwords or something. So I have your entire contact list, and I will send them this and that, and blah, blah, blah. Now, obviously, I had nothing to worry about. But I was very concerned about this email because they included a password that I had used many years ago, and it was a very difficult password to remember. It was a combination of lowercase, uppercase letters and numbers. Did not have any special symbols, but it was also only 8 characters long. Okay, and I went to the website that Alex showed us the other day, the Have I Been Pwned or Pawned or whatever, and I checked it out, and it said that there was exactly 1 breach with that password. So somehow, somewhere in the last many years, I think I've been using this password for a very long time. I haven't used it recently, but I've been using some modification of it pretty recently, which certainly concerned me. And so I showed the email to my wife, and I was like, oh my goodness, we've just gone through security in this class, and we've gone through Bitcoin, and then I also Googled some text from this email, and it turned out it was a rather large scam that started yesterday. In fact, one of my friends on Facebook also reported that he had the same thing happen to him, and same concern that a specific password was revealed or known to this scam. And then a few hours later, my wife got a similar email, except that hers did not have a password in it, but it also had an email address that she has been using or whatever, right? So indeed, coming back to Alex's point, it's really important to make sure that you have good password hygiene, right? Keep your passwords long, have them generated by a password manager, perhaps store them in a password manager. There are some pretty popular ones out there. There's LastPass, 1Password, KeePassX. In fact, even some popular browsers like Edge and Google Chrome have a password manager built into them, which means that what is securing the passwords in those browsers is your Google or Microsoft login or Safari login or whatever it is.
I have a question.
Sure.
Is that website on the doc?
No, Alex, could you add it, please? The Have I Been Pwned thing.
I will.
Yeah.
Yep.
And that's a legit website. I mean, it's pretty widely known, so it's not like by entering your password, you're giving it away. So anyway, I just thought it was interesting. So, okay, coming back to what is Bitcoin. So Bitcoin is this idea that, so by the way, before I get to Bitcoin, if you guys ever come across such a scam, for heaven's sakes, please don't pay any ransom money to anybody, okay? Tell your parents, or if you're an adult already, please understand that this is likely a scam. Go Google the particulars of that particular issue. And then if you believe that you have been not as good with your passwords, then take that opportunity to start getting good, right? It's better late than never. So since yesterday, sadly, I have been diligently going through, taking Alex's advice and trying to update some of our critical accounts and making sure that we are well secured. So hey, this class has been interesting to all of us, I guess, including to me, because I was at least reminded and had this unfortunate thing happen to us yesterday, where fortunately there have been no repercussions of it at all, but it's an opportunity to get better, to get smarter, right? Which is always a good thing. Okay, so what is Bitcoin? Bitcoin is the currency of the devil. No, I'm just joking. But it's from a computer science point of view, it's a really interesting idea where you're using this idea of security, public-private keys, hashes, blockchain, which is a building up of security protocols and hashing to make a tracking and record of transactions. And Bitcoin is not issued by governments, which is typically how money is issued, right? This notion of currency, which is backed by either a gold standard or currency that is at least backed by the guarantee of a government, therefore called fiat currency. Unfortunate word, as Alex said, but still a term in economics that's widely understood and known. So certainly Google that FIAT currency. And Bitcoin is this idea of saying we don't need no government to tell us how to run our lives. We're going to have our own currency, and we're going to have it generated by computers because computers are impartial. But obviously, to have something be currency, it has to be unique. It has to be scarce, otherwise it won't have value. And it has to be just like really hard, and there has to be some way of generating it, right? And so these people who came up with these algorithms for generating Bitcoin were pretty smart. They said there has to be this concept of a proof of work, which means that your computer or bank of computers should have solved a specific problem. The problem is very much analogous. It's a lot harder than solving a Rubik's Cube, but it's very analogous to a Rubik's Cube in the sense that really hard to solve, really easy to verify that it was solved. And so when you think you solved it, you send it out to the entire network and you say, hey, I think I solved it. When you solve it, you get 12.5 Bitcoins in return, or some number about thereabouts. Every time you solve it and somebody gets paid, which is very rare because this is very, very computationally hard to do. That person gets paid, or that data bank of computers get paid, and then the next problem is generated by the system and spread out to all the computers in the world that are working on mining Bitcoin, right? And the complexity of the problem increases, the reward reduces, and thereby there's this idea of slowing down the rate at which Bitcoin is generated over time. That being said, it is expected, or it is known, that the total value of Bitcoin in today's market at about $6,850 US dollars per Bitcoin is about $110 billion, $120 billion of Bitcoin that exists in the world. Amazingly, and I don't think I said this before, about 20% of that has been lost because people, lost their public key or private key. They lost a computer that had mined it, random stuff like that. On the other hand, there have been a bunch of people who completely speculated in Bitcoin and made a ton of money. So, your mileage may vary, kind of thing, right? So pretty fascinating concept, very interesting. Bitcoin isn't the only cryptocurrency out there. Other things as well. And if you guys have any interest in studying that further, certainly use almighty Google to find out more. Go to Coinbase, which is an exchange for Bitcoin, just one of many exchanges, in fact. And check it out. And then there's some philosophical concerns around Bitcoin, which, certainly Alex and I share those concerns. But a lot of people are like, let's go speculate. Let's go do some stuff. And hey, I guess more power to you, literally, because it's going to take you that much more power to process these things anyway. I'm just joking about that one. But yeah, and then everyone should have a password manager. Remember that. That's coming back and tying back to the concept of security and privacy. The more complicated your password is, the lower the chances that it's ever going to be broken. But as we know, with really capable computers these days, if you're not careful, you can get quite in a bit of trouble. Yeah. Okay. Theory. Back to Alex.
Yeah. So I presented two aspects of computer science theory. One is computability. What is a problem that can be solved? What does it mean for a problem to be solvable with a computer? And I talked about the work by Alonzo Church and Alan Turing in the 1920s, almost 100 years ago now, defining computability in terms of equivalent ways of expressing a mathematical algorithm, expressing a mathematical computation. The two that Alonzo Church worked on initially were theory of recursive functions, and the second one was lambda calculus. Two different ways of doing math, completely different, but he could prove that he could always translate a recursive function into a lambda expression. He could always translate a lambda expression into a recursive function. And so he came up with this idea. He said, probably there's only so much that can be done with ways of expressing math. Any way of expressing math that I could think of is going to be equivalent to these two, or less powerful, but it's not going to be more powerful than these two. And this was the Church thesis. Turing came along and said, okay, but these are not computers. These are ways of writing math on a blackboard. Let's come up with something that looks kind of like a real computer from the perspective of a mathematician in the 1920s that didn't really have transistors, didn't really have electronics. So he came up with the idea of the Turing machine. The Turing machine has never actually been built. There's no company that makes Turing machines, but it could be built, and software has been written that performs the work of a Turing machine. So Turing machines don't exist as boxes that you can buy off of a shelf, but you can certainly really work with a model of a Turing machine using software. And he came up with this idea of a way to build a computer, and he proved that he could take any lambda expression and translate it into a Turing machine basically into a bunch of electrical switches and wires and a tape. And vice versa, for any Turing machine, so for any bunch of switches and wires and a tape, he could correspondingly come up with a lambda expression that did the same thing, that computed the same result. And so he proved that not only were different ways of expressing math equivalent to one another, but even computers could be proved to be equivalent to the way of expressing math. And so he came up with an extended version of Church's thesis, which is any computer is only going to be as powerful as the Turing machine, or less powerful, but not more powerful than the Turing machine. So any problem for which there is a Turing machine that can solve it can be solved with some other computer, any other computer. Any problem that can be solved with any computer can be solved with a Turing machine, but there is no problem that cannot be solved with a Turing machine, but that could be solved with some other computer. This is very important. He proved that there were problems that could not be solved with a Turing machine, and he assumed, he made this assumption, that if they cannot be solved with a Turing machine, they cannot be solved with any other machine, with any other computer. Fundamentally, Turing's thesis cannot be proven, but it has held so far. In other words, no type of computer that humanity has come up with has proven to be more powerful than the Turing machine. And there are very strong reasons to believe that Turing machines and present-day computers, which are equivalent, are really the maximum of computing power in terms of what problems can be solved and what problems cannot be solved at all. Now, among the problems that theoretically can be solved, there are problems that can be solved in a short time and problems that would require trillions of years to be solved. Now, if a problem requires 1 trillion years to be solved, yes, theoretically it's solvable, but in practice we can't really wait that long. So there's a question of determining which problems can be solved in practice and what problems cannot be solved in practice. And that's where complexity theory comes into play. Complexity is the measure of how much time a computer needs to solve a problem. Now, complexity is a priori a property of software, not of a problem. So I can always write a very slow program to solve a problem. I can always add useless math, useless work to my algorithm to make it slower, but I can only make it so fast as it can be made, right? There's a limit to how fast it can be made. There's no limit to how slow it can be made, but there is a limit to how fast it can be made. So when I solve a problem in the best possible time, I've identified the best possible complexity for that problem. Okay, and so problems have a best complexity, a best execution time. When the execution time, and the execution time generally depends on the size of the problem. Yeah, for a given class of problem, it takes longer to solve a bigger problem than a smaller problem. Think of the addition of numbers. When you were in, I don't know, second grade, first grade, you were doing 1-digit numbers and 2-digit numbers. And then, in third grade and fourth grade, you were doing 4- and 5-digit numbers. Obviously, it was more work to do the addition of a 5-digit number. So that problem, adding numbers, is a linear problem. Say that it takes you a second or 5 seconds or some number of seconds to add 1 digit. Well, if you have 5-digit, it'll take you 5 times longer. This is linear. Linear is good, right? It's easy to solve linear problems. Then you have polynomial problems. P stands for polynomial. Polynomial means that it might take you the square of the number of elements in your problem to solve the problem, or the cube, or the 4th power. As the power increases, it becomes harder and harder, but we generally consider polynomial problems to be solvable. Problems that are not in P, that are not polynomial, whose complexity is not a polynomial, they might have an exponential complexity. Exponential means that they're very, very hard. It means that it might take the age of the universe to solve even a smallish problem. Some of these problems that are exponential could be polynomial if we had a computer with infinitely many cores. These problems that are polynomial if we had infinitely many cores are called NP, non-deterministic polynomial. It would be really cool if we could take an algorithm to solve an NP problem and convert it into a polynomial algorithm, right? It would make a lot of real-world problems a lot simpler than they are today to solve with a real computer. To this day, it is unknown whether NP problems are really P. In other words, whether there is a real algorithm that would take a polynomial time to solve a non-deterministic polynomial problem. We know that they can be solved in polynomial time using infinitely many cores. We don't know whether they can be solved in polynomial time using a small number of cores, using a finite number of cores. If one of you guys wants to pursue a PhD in computer science or not, but whether you do or not, if you could answer this question, whether P is equal to NP, there's a Nobel Prize for computer science waiting for you. It's called the Turing Award, and it's really, really cool. So these are the two definitions of what can be done and what cannot be done with computers. The first one is absolute, right? There's problems that can be solved theoretically and cannot be solved theoretically. If they cannot be solved theoretically, good luck. And then there's the question of what can be done in practice, and that pertains to complexity theory. That's about as much theory as I think is appropriate for this class.
All right. So, folks, we are done. And I'm wondering what is Alex and I going to do? What are we going to do every evening now? But I'm sure we'll find something. So with that, we want to thank you guys for coming diligently every evening. If you have any questions, we're happy to take them. And with this, you conclude your first Stanford class, and hopefully there'll be many more for you all.
Thank you.
Thank you.
Thank you.
The class.
Thank you.
All right, you're most welcome.
I'm on YouTube.
Thank you.
All right, bye guys. Take care.
Thank you so much.
Bye. Thank you.
Thank you.
Thank you.
Thank you.
You're welcome. Alex, you want to stop recording?
Thank you.
I'm proper.
Thank you.
Will you be keeping the docs on, or will you be deleting the doc?
No, I'll keep it. I mean,